Symmetric matrices. Welcome, everyone. Today, we are going to explore a very important concept in linear algebra called symmetric matrices. Before we dive into the formal definition, there is a fundamental prerequisite you must understand. The property of symmetry applies exclusively to square matrices. To ensure we are all on the same page, let's recall what that means. A square matrix is simply a matrix that has an equal number of rows and columns. For example, a 2 by 2 matrix or a 3 by 3 matrix are both considered square matrices. Keep this requirement in mind, as it is the first thing you should check before determining if a matrix is symmetric. Now that we have established this foundation, let's move forward to the formal definition. Definition of a symmetric matrix. Now that we have established that this property applies exclusively to square matrices, let us move on to the formal definition. A square matrix, which we will call matrix A, consisting of elements a sub ij, is defined as a symmetric matrix if it is exactly equal to its own transpose. To express this in mathematical terms, a matrix A is symmetric if a prime equals A. In this context, a prime, which you may also see denoted as a transpose, represents the transpose of the original matrix A. Essentially, if you flip the matrix over its diagonal and it remains unchanged, it is symmetric. In the next few slides, we will look at how this works on an element-by-element basis and how to visualize this symmetry. Element-wise condition for symmetry. Now, building on the definition we just discussed in the previous slide, let's look at what this means for the individual elements within the matrix. If the transpose of matrix A is equal to matrix O itself, then a very specific condition must be met. Specifically, the element located in the ith row and jth column must be identical to the element located in the jth row and ith column. To express this mathematically, we state that a sub ij equals a sub ji for all possible values of I and j in simpler terms. This means that if you swap the row and column indices of any element, you should find the exact same value at that new position. Understanding this element-wise relationship is crucial, as it leads us directly into how we can visually identify these matrices, which we will cover in the next slide. Visualizing symmetry. First, in a symmetric matrix, the elements are mirrored across what we call the main diagonal. To identify this, simply look at the diagonal line that runs from the top left corner down to the bottom right corner. It is important to note that the elements sitting directly on this main diagonal can be any value. They do not need to follow any specific pattern or match any other number to maintain the symmetry of the matrix. The key requirement is that the elements located above the diagonal must be a perfect mirror image of the elements located below it. If you imagine folding the matrix along that main diagonal, the corresponding numbers on either side should overlap exactly. Now that we have established the mathematical condition for symmetry, let us move on to how we can visualize this property within the matrix. Understanding this visual pattern will make it much easier for us to follow the step-by-step identification guide that we will cover in the next slide. Step-by-step guide to identifying a symmetric matrix. First, we must check the dimensions of the matrix. As we mentioned at the start of this lesson, symmetry is a property that applies exclusively to square matrices. Therefore, your first step is to ensure the matrix has an equal number of rows and columns. If it is not a square matrix, it cannot be symmetric, and you can stop right there. Second, we need to find the transpose. To do this, you simply swap the rows with the columns. This new matrix is what we refer to as a prime or a transpose. Third, we perform a comparison. You will take the original matrix, A, and compare every single element with the corresponding element in the transpose, a prime. This is essentially checking if the element in the ith row and jth column is identical to the element in the jth row and ith column, as we discussed in the element-wise condition. Finally, we can draw our conclusion. If matrix A is exactly equal to matrix A prime, then the matrix is confirmed to be a symmetric matrix. However, if you find that even one single element differs between the two, the matrix is not symmetric. Now that we have a conceptual understanding of what a symmetric matrix is and how it looks visually, let us walk through a formal, step-by-step process to identify one. To see this process in action, let us move to the next slide and apply these 4 steps to a practical example. Illustrative example. Please look at the screen. We are asked to verify if matrix A is symmetric. Matrix A is a 3x3 matrix where the first row contains 2, 3, and 5, the second row contains 3, 1, and 0, and the third row contains 5, 0, and 4. To solve this, we will follow the step-by-step guide we discussed in the previous slide. Step 1 is to check the dimensions. As we can see, the matrix has 3 rows and 3 columns. Therefore, it is a square matrix. This is a vital first check because, as we learned in the introduction, a matrix must be square to even be considered for symmetry. Step 2 is to find the transpose, which we denote as a prime. To find the transpose, we simply swap the rows with the columns. We take the first row 2, 3, 5 and write it as the first column. Next, we take the second row 3, 1, 0 and write it as the second column. Finally, we take the third row 5, 0, 4 and write it as the third column. After performing these swaps, we find that a prime is exactly the same as our original matrix. Step 3 involves a detailed comparison of the elements to ensure they are mirrored across the main diagonal. We check the element in the first row, second column, which is 3, and see that it matches the element in the second row, first column, which is also 3. Then, we look at the element in the first row, third column, which is 5, and find it is identical to the element in the third row, first column, which is also 5. Lastly, we check the element in the second row, third column, which is 0, and see it matches the element in the third row, second column, which is also 0. Finally, in step 4, we reach our conclusion. Since the transpose, a prime, is equal to the original matrix A, we can officially state that matrix A is a symmetric matrix. Now that we have covered the theoretical definition and the visual properties of symmetry, let us apply that knowledge to a practical example. Real-world application: distance matrices. Now that we have mastered the mathematical process of identifying symmetric matrices, let us explore how this concept is applied in real-world scenarios. A very common example of a symmetric matrix is what we call a distance matrix. To illustrate this, imagine we are tracking the distances between 3 different cities. City X, City Y, and City Z. If we construct a matrix where each element, which we can refer to as a sub-ij, represents the distance from city I to city j, the resulting matrix will always be symmetric. The reason for this is quite intuitive. The distance from city X to city Y is exactly the same as the distance from city Y back to city X. This inherent reciprocity is what creates the symmetry. Let us examine the example provided here in matrix D. In the first row, we have the values 0, 10, and 15. The second row contains 10, 0, and 20. Finally, the third row contains 15, 20, and 0. If we apply the mirroring rule we discussed in the previous slides, we can see that the element in the first row, second column, denoted as sub-12, is 10 kilometers. Similarly, the element in the second row, first column, D sub-21, is also 10 kilometers. Because these corresponding elements are identical across the main diagonal, matrix D is a symmetric matrix. Understanding this practical application helps solidify the concept, but before we conclude the lesson, it is vital to discuss some common mistakes students make when dealing with symmetry, which we will cover in the next slide. Common mistakes to avoid. First, let's talk about non-square matrices. A frequent error is attempting to check for symmetry in rectangular matrices. Please keep in mind what we established in our introduction. Symmetry is a property that applies exclusively to square matrices. If the number of rows and columns is not equal, the matrix cannot be symmetric. Next, be careful not to overthink the main diagonal. Some students mistakenly believe that the diagonal elements must be the same number or follow a specific mathematical pattern. However, as we discussed during our visualization of symmetry, the elements a 1, 1, a 2, 2, and so on can be any value whatsoever. These diagonal elements do not affect the symmetry of the matrix. Only the mirrored elements around them matter. Finally, it is crucial that you do not confuse the transpose of a matrix, which we denote as a prime, with the inverse of a matrix, denoted as a inverse. While both are important matrix operations, symmetry is strictly and only concerned with the transpose, the process of swapping rows and columns. Now that we have seen how to identify symmetric matrices and how they appear in real-world scenarios like distance matrices, let's discuss some common pitfalls to ensure you don't make these mistakes in your exams. By avoiding these 3 common mistakes, you will have a much firmer grasp of the concept. Now, let's move to our final slide to summarize the key takeaways of this lesson. Key takeaways. First, the fundamental definition. A matrix A is considered symmetric if its transpose, which we denote as a prime, is equal to the original matrix A. In more detail, this means that the element-wise condition for symmetry is that the element in the ith row and jth column must be identical to the element in the jth row and ith column, for all possible values of I and j. As we emphasized at the very start of this session, please remember that symmetry is only possible for square matrices. If the matrix is not square, it cannot be symmetric. Finally, from a visual perspective, you can quickly identify these matrices by checking if the elements are mirrored across the main diagonal, which is the line running from the top left to the bottom right of the matrix. To wrap up our lesson on symmetric matrices, let's review the key takeaways to ensure you have a solid understanding of the concept. Keep these points in mind, and you will be able to identify and verify symmetric matrices with confidence.